Hello everyone. Today we're going to uh, learn Fourier series in a little bit more systematic way. We have been looking at using the normal modes of a string that's under tension, and we look at its normal modes, like this is the lowest mode, and then we had this mode, and so on and so forth. And these modes, we said, well, we can use these modes to actually construct any shape of this string. So if this string was length L, and this also length L, but this string was in some arbitrary shape. So one of the examples we did was this, and it turns out this function, if you write as a function of, say, this is x, and this x equal to 0, and this x equal to L, and this is a function of x. So this function I could write using the normal modes, and the way we did was the modes were written as functions normalized way, and we'd written phi n was equal to some normalizing function, and then as a sign of knx. And what is kn? Kn was n pi over L for this problem, and the n we made sure the unique numbers of 1, 2, 3, and so on and so forth. And the normalization was obtained by demanding that if I have phi n or phi m, and I integrate it over, the smallest one is pi over L. If you put pi over L, this had a period of 2L. So we did over a period, it says 0 to 2L, but this is a period. So this is the period of the mode with n equals to 1, and so the smallest k, the period corresponding to the smallest k. So we said this should equal to 1, and that said, well, if n equals to m, and it should be 0 if n not equal to m. But the 1 was used to normalize, so if I put it there, I get n square 0 to 2L sine square knx dx, and I demand that to be 1, and I work this out. One way to work this integral out was to divide by 2, multiply by 2, and this write as a using a double angle formula, like cosine 2 theta equal to 1 minus 2 sine squared theta. So if I have a sine square of this angle and I have 2, then I can write 1 minus cosine 2 knx. And when I integrate over this, it's multiple periods of this function, and so this will give me 0. So I get n square over 2 times 2L for this, and then I have a n is square over 2, 0 to 2L cosine 2knx dx, and this gives 0. So if you look at this, n is 1 over square root of L. So these were the normalized modes, and we said we have this function x, then we could construct using, it's the same system, so construct using the normal modes. So we wrote down for I don't know how much of each I need, so some amplitude or some coefficients of phi n of x, and I just include all the modes 1, 2, 3 to infinity, and I need to figure out how much of each I need. And so there was a trick we did. We said, okay, I know this integral, so I can use that. So I had fx times, say I want n equals to some m, so phi m of x dx, if I multiply and integrate and integrate over one whole period, then this turns out to be on the right side, 1 to infinity. Phi m is one of these guys, which is going to be an phi n of x, phi m of x dx, and then the integration can go right through the term by term, and 0 to 2L. Well, when I do it out, it's only one of these term is non-zero. So this is going to be n equals to 1 to infinity an, and this is either 0 or 1. You can use what is called Kronecker delta to indicate this, so-called indicator. So nm, and it's only when n is equal to m. So I'm going over all the n values, and n equals to m, and that's when this is 1, everywhere else 0, so this just be am. So we have a rule for am is 0 to 2L fx phi m x dx. So we did have when we say that, we say expanding using the normal modes. So we expanded an arbitrary shape f of x into the normal modes phi n of x. In Fourier series, what we're going to do is we are trying to handle start with what kind of functions we can expand into a particular types of these functions. So in Fourier series, what we do is not arbitrary shape that way. We would say we have a periodic function. It's about expanding a periodic function. So, and this is an arbitrary periodic function. Periodic functions of, say, f of x, say of period L. We could say t, but when we use x, we use the letter L. When this is t, we use the letter big T for that. So that's the language for saying what kind of periodic function we have. So this is if x was a space, this would be like a period in space, or you might say this is a wavelength. And So this will be a regular period, but we use the same language regardless of what property we are looking at. So if there's a function, which is a periodic function, but L into appropriate sines and cosines. So what are these appropriate sines and cosines? So these sines and cosines they have periods which are inverse multiples of this period. So you'll have sines and cosines of periods L, L over 2, L over 3, L over 4, and so on and so forth. So we're going to do that in the next video. So I'm going to stop here, see how far we got.